Hello everyone. If you have watched the videos I shared before, you will notice that I have mentioned Uni 3C multiple times, because it introduced an approach to generate camera control and pose control videos through 3D methods. It is divided into two parts, camera control and character animation. First, perform point cloud scene reconstruction based on reference images, set up camera animation, and output camera control videos. Second, perform SMPL and Hamer sequence model reconstruction based on reference videos and output pose control videos. These two modules have already been integrated into KJ's WanVideo wrapper. In recent updates, camera control can not only be used with image-to-video models, but can even be used with VACE as well. However, since obtaining SMPL and Hamer control videos is very difficult, the character animation control module is rarely used. Today I will share a method that also follows the Uni 3C approach, but provides a more convenient way to achieve camera control and character animation control. What you are seeing now is a motion capture tool for ComfyUI. This tool can identify character animation in videos and generate SMPL sequence models. It is equivalent to a simplified version of Really's Dance. The name of this tool is ComfyUI Motion Capture. What we need to use is its SMPL recognition and sequence model generation module. The motion capture tool requires a relatively unique environment. To be safe, we will create a separate ComfyUI package. Instead of using Miniconda to create multiple environments, I use the most basic method of splitting directories. I created a motion package and installed the motion capture tool along with related utilities. Please note that the motion capture tool creates an output directory in the ComfyUI root and saves its intermediate files there. The author did not save the output files to the default output directory. In this directory, we will find .bin files with names starting with SMPL mesh. These are the intermediate files we need, containing the SMPL model sequence. Let's open the SMPL generation workflow. It's the same as the default workflow provided by the author. The difference is that I use the compare SMPL versus BVH node. Please note, I did not use the latest SAM 3D body here, because this node cannot generate model sequences. It only generates skeletal animations. This is a video clip we're going to process. It's a traditional Chinese Tai Chi movement, a total of 301 frames. This mass video was obtained using SAM 3, and I won't elaborate on it here. Once the original video and mass video are ready, SMPL recognition can be performed. Alright, let's run it. The SMPL 3D viewer node reconstructs the model for each frame based on SMPL data. Therefore, the animation playback is very laggy. The compare SMPL versus BVH node, on the other hand, converts SMPL data into a model sequence file. During animation playback, it loads and displays the model corresponding to the current frame, which is very fast. In this way, we have achieved character animation based on video. So what should we do next? How can we apply this in video generation? First, we find the SMPL mesh.bin file just generated in the output subdirectory of the ComfyUI root directory. It contains the SMPL model sequence, which is our character animation asset. Please note, the motion capture process is complete. The following operations do not need to be done within the motion capture ComfyUI environment. What you are seeing now is a node I created called the Advanced 3D Viewer. It is a 3D viewing tool based on 3.js and WebGL. We will use this node to import the SMPL animation asset just created and also create a camera animation. Copy the path of the .bin file and import it into the scene. Reset the camera's positive y-axis to restore normal camera control. Dragging the timeline slider allows you to see the model sequence playing correctly. Set the start and end frames according to the scene animation. Adjust the frame resolution as needed for the video, for example, 640 by 640. You can see the real-time update in the info bar. Reduce the FOV and lock onto the subject. Create a camera based on the current view and enable auto keyframing. Changing the viewport will automatically create keyframes for the camera. Next, create a camera keyframe for the end frame. Enable animation playback state for observation. The middle part is not ideal. Exit the animation playback state and add another keyframe. This way, I have completed a camera animation. This scene contains both character animation and camera animation. In fact, this part of the operation is the same as the animation preview in traditional 3D production pipelines. However, to allow Uni 3C to recognize the camera motion, we need to create some key information. Enable ENV to create a background environment, add a ground plane, and random boxes in the background. The white dots on the ground and the boxes in the background provide Uni 3C with sufficient sample points. They are equivalent to camera tracking points in the 3D production pipeline. You can refresh the floating boxes in the background several times to get the most ideal result. I forgot to demonstrate one step. We should adjust the light direction and intensity to make the character's outline and facial features clearer. Click the recording button to record our animation as a WEBM format file. This video, besides being directly used to control camera motion, will also be used next to extract skeletal animation. Please note, we can also save the scene with completed camera animation as a GLB format file and import it for editing anytime. Open the video control workflow located in the module subdirectory. It includes various pose acquisition methods, such as Control Net Preprocess, Animate, Steady Dance, SCAIL, and One-to-All. Load the video just generated. Please note, I converted it to MP4 format. Regarding the redirection image, I took a shortcut and directly used the first frame of the original video because it is almost the same as the first frame of the control video. Of course, you can also choose a character image to which you want to impart the animation, or use the first frame of the control video to generate via ControlNet. The post-control videos are all generated. Please note, for Control Net Preprocessing, I enabled both depose for body pose and open pose for facial pose. Animate and Steady Dance use the same pose control video, but Animate has 3 additional control videos. The acquisition methods for One-to-All, as well as Animate and Steady Dance, are all based on depose and can be used interchangeably. In fact, the control videos for Control Net Preprocessing, Animate, Steady Dance, and One-to-All are all interchangeable. I personally prefer SCAIL because it incorporates NLF pose. The MTV crafter I introduced before uses NLF pose. It introduces the so-called concept of 4D pose. This means it adapts according to the varying bone lengths of different characters, which is an advantage. SCAIL also incorporates D-pose to obtain facial and hand poses. Except for the control net pre-processing method, the other three methods all include a retarget function. That is, they move the skeleton obtained from the video to the position of the character in the retarget image. With this, our preparatory work is complete. We have obtained the camera control video and the pose control video. Next, we can proceed to generate the video. In this update, besides adding Uni 3C support for the VACE long video generation workflow, I have also added long video generation workflows for Animate, Steady Dance, One-to-All, and SCAIL. For example, the currently opened Animate workflow. Regarding the use of the long video generation workflow, I have a dedicated video introduction. If you're interested, take a look. When using the SCAIL pose control video, please note that its resolution needs to be changed to half of the output resolution. Otherwise, it may cause the output to turn dark. If it still occurs, then do not use the pre-processed video, but obtain it directly from the original video. Or change the seed number and regenerate. VACE motion restoration is quite good, but I found it has quite a few restrictions during testing. First, its base precision cannot be BF16. It can only be FP16 or FP16 fast. Second, it prefers portrait resolution, meaning a vertical frame. Third, it only supports a single window, and if it's less than 81 frames, it will automatically be padded to 81 frames. Additionally, I personally feel its completion for females is better than for males. A major issue is that its restoration and consistency of the reference image are not ideal, which contradicts the official examples. But it might also be due to my parameter settings. Furthermore, to make OTA follow the prompt, the CFG needs to be set to 2.0 or higher, requiring longer generation times. It requires more CPU and GPU resources. Steady Dance does not support Uni 3C. An error will occur if they are used together. Now, let's compare the generated results. In terms of reference image restoration, SCAIL, Animate, and Steady Dance are all good. However, as the number of windows increases, the patterns on the clothing in all videos change significantly. In terms of pose restoration, SCAIL is the best. Animate and Steady Dance show errors in character proportion and structure by the third window. In VACE 2.1 has a persistent major issue with identifying the front and back of characters. Regarding camera animation, except for Steady Dance, the other four restore it perfectly. Another set, same action, different camera, similar conclusions. Please note, the current biggest flaw of the SMPL motion recognition solution is the restoration of facial and hand poses. It can be seen in this video that the hand movements differ greatly from the original video. Compared to the Really's Dance solution, the current solution lacks the hammer tool for hand motion recognition. For the two SCAIL cases you see now, I used model animation assets from a traditional 3D production pipeline to generate the preview. Please note, the preview in this example was also created in the advanced 3D viewer, but can also be generated directly in 3D production software. The reference image restoration is quite good, but as the number of windows increases, especially when turning to the character's back, details are severely lost. When switching windows, the action jumps, which is hard to avoid in SCAIL, plus Uni 3C long video generation. Unless you don't use Uni 3C and instead use context windows for long video, you cannot guarantee smooth action. By the way, the models and animation assets I used were downloaded from Mixamo. Finally, let's look at the operational workflow I summarized. The first two steps are to obtain the animation model sequence from video via SCAIL and create camera animation, or directly utilize model animation assets and create camera animation. Then, acquire the pose control video to generate the final video. Thank you, everyone. I hope this sharing has been inspiring for you. Finally, let me introduce the Advanced 3D Viewer tool. It supports importing embedded GLB, embedded binary or ASCII FBX, SMPL bin cache, OBJ-PLY. It supports GLB, GLTF, and FBX files that contain object, camera, and light animations. It supports zip archives containing external assets. It can automatically load the GLB or GLTF file within, along with its corresponding external textures and bin file. It can automatically load the external textures corresponding to the FBX file within zip archives. It can automatically load the OBJ file and its corresponding MTL material file and textures within zip archives. For example, this embedded GLB file. Or this zip archive containing a binary FBX and its corresponding textures. You can switch between built-in materials and adjust the properties of the current material. The built-in materials include wireframe, normal, depth, 4 types of outlines, and 2 types of AO. When switching to the depth material, you need to press the Focus to Depth button to automatically adjust the depth range based on the model size. We can capture the current screen by taking a screenshot. By pressing the Get 3D Data button, you can export a package containing the 6-sided 3D data of the currently selected model or the current scene. If you're interested, you can check out my previous series of videos on image-to-model generation to learn how to use this data to generate diverse textures for meshes. The archive contains 4 directories: original textures, normal, depth, and outlines. Please note, during the demo, I forgot to adjust the frame to square, which is a mistake. Thank you again, everyone.